Hey guys, Mr. Wood here. Going to do a short lesson, continue on in chapter 7. I'm actually, you can tell I'm not at school, I'm at home. And but I wanted to get this lesson something you guys can watch on Monday. And really, I'm hoping by the time we do our first full Google Meet on Tuesday that you guys will have looked through the stuff I posted on chapter 7. I don't have any jokes for today because I'm at home. I don't have my jokes with me. Let's see. Do I got a silly little joke? Okay, you guys are gonna groan when you heard this, but why was 6 so scared of 7? Because 7, 8, 9. You've heard that. And you go, that's not very good. And then this one's not any better. If 2's company and 3's a crowd, what are 4 and 5? 9. 9. So there you go. Okay, today again, it's not going to be a long lesson, and I'm going to try and get us caught up on the main things on Tuesday. And I know I'm going to wrap up chapter 6 too. Some of you have already done that. Some of you need to do that. I've got behind me on the board, and this is on your formula sheet right there on the and I told you this in earlier lessons, but if you go back to your formula sheet here, what it says right here, I would write all these down. Okay, and actually today I'm going to do, I think it's kind of a cool equation, almost more of a physics thing. And again, this chapter is on atomic structure, and it's on then the periodic table, and of course, you could say, well, we're talking about waves, which are more of a physics thing. And the reason we're going to talk about waves is how light interacts with especially electrons and how electrons emit light, which we're going to get to on Tuesday. And that's why light exists in the form of waves. And so on the test we'll take, which will be technically the final, which will be the chapter 7 test, which I'm still kind of figuring out what I want to do on that, being we're remote, but we'll do that. There will be a little bit of this, but it's not going to be the main point. Again, it's going to be more reviewing electron configurations, atomic structure, and then making some predictions on periodic trends. And we'll come to all that here in the next 2 weeks. But real quick, these equations I would write down again. This is already on the formula sheet. C is the speed of light, frequency times the wavelength. E is energy, H is another constant, so C is a constant, H is a constant, it's called Planck's constant, times frequency. And then if I just rearrange and plug in for frequency, which equals speed of light over the wavelength, energy equals Planck's constant times the speed of light over the wavelength. And then if we rearrange that, wavelength is equal to Planck's constant over mass times C. And where that came from, I talked about this in the last video, this came from equals mc squared along with this equation here. And again, I would just write that down. And then if I rearrange this, we get that. Okay, so then back to the notes. Okay, so where we were at in the chapter, and I think it's always kind of interesting in this chapter at this point that we talk about Einstein a little bit, and of course Einstein is incredible, famous scientist, and but what he won his Nobel Prize for, it was not for E equals mc squared or anything else. It was for the photoelectric effect. And so if we kind of combine, and we went through this slide, I think we've talked about it, but the dual nature of light. Light has both wave and particle-like properties. So light acts as a wave, and that's what that diagram there is showing, the waves and the wavelength. But then I got under, it looks like baseballs or billiard balls. But light also acts as a stream of particles. And so Einstein said light acts as a particle. He got that from the photoelectric effect, but then light acts as a wave. It has all the characteristics of wave. Well, almost 100 years ago, this guy named Louis de Broglie reasoned that if light could behave like a particle, then electrons, which until now were considered to be a particle, could have wave-like property. And there's de Broglie. And the equation I got was right here. Okay, so then we come up with this, and this show you this calculation, and I think this is kind of fascinating how this works. So we're going to do this. We're going to compare the wavelength. So I am going to use, and I'll write this out, I'm going to use the fourth equation here of an electron, and we've got its mass and how fast it's traveling versus a ball. Okay, so that's the calculation we're going to do here. Okay, now one thing to note, and I always go back, so we're going to use this fourth equation, is the units. And this is something maybe to write down on your formula sheet in that same place. And I can tell you though, I don't think on the test I'm going to have a problem like this. I'm doing this just because it's kind of fascinating to see how it works. But 1 kilogram meters squared over seconds squared equals a joule. And that might be worth writing down on your formula sheet. Okay, so if I do the and I'll show you now, and just like I've done hopefully all the way through the class up to this point, is how we do this with the units. So for an electron, we're trying to find its wavelength. So again, I am using this equation right here. So I'm going to plug in the units for Planck's constant. So I've got 6.63 times 10 to the negative 34th. Remember, it was joules times seconds. That's the unit. Well, I'm going to plug this in for joules. So I've got kilograms, meters squared, seconds squared, times seconds. Okay, because remember, this is a joule per second. Okay, and then I'm given the mass. And the mass was 9.11 times 10 to the negative 34th kilograms. And the speed of an electron is moving pretty fast, 1 times 10 to the 7th meters per second. Okay, that's meters per second. Okay, so this was what was given in the problem. This was the mass and this was the speed. Now watch the units. So kilograms go. 1 of the meters go. 1 second goes here and 1 second goes there. And what I'm left with is in kilograms. And remember, we were trying to find the mass. So you should punch this on your calculator. And what I get here is 7.3 times 10 to the negative 11th meters. And again, this, I would write it down. And this is, again, is something that if you take physics, you would use that. In chemistry, we really won't use it past this, at least in my memory. Okay, so that's an electron. So this is the wavelength. Whoops. I'm sorry, I had the wrong unit. It's meters. I went through all that with units and then I messed up. Kilograms had canceled out. What I was left with was meters. So there's the wavelength of an electron, 10 to the negative 11th. That's really small. Well, let's compare that then to a ball. So again, I'm going to do the wavelength is 6.63 times 10 to the negative 34th. And again, it's kilogram, meters squared, seconds squared, times seconds, because that was part of Planck's constant, over 0.10 kilograms. And it's not moving nearly as fast, 35 meters per second. So again, watch what happens with units. So kilograms go, 1 seconds go here, the other one goes here, and then that cancels out, so I'm left in meters. And this comes out to be 1.9 times 10 to the negative 34th meters. So that's the wavelength of a ball. Well, we said that was a small wavelength. Well, look at that wavelength. That is really, really small. Okay, so what can be derived then is this. So this is what can be derived then. I've got, here's my eraser. So in that calculation, so I'm going to erase this. So this is what physicists and chemists come up with. So if we've got a continuum and we've got a large mass, And then we've got a small mass. And then we got in between. So here would be electrons. They would kind of be between those. Here would be like me. Mr. Wood, we know, has a very large mass, unfortunately. And a small mass would be like light. Okay, so large mass, small mass, okay, and different things on the continuum. Here, this is going to behave mostly like a wave. And that's what the calculation said. Over here, a large mass is going to behave mostly like a particle. Can you believe your big old fat AP chemistry teacher has a little wavelength? And then here is wave and particle-like behavior, kind of in between. So what this says, this calculation says, is something that has a very, very small mass, like light, is going to behave mostly like a wave. Something with a large mass, like we did in this problem, what was it, a ball, it's going to behave more like a particle, and then in between has wave/particle behavior. So I don't know, I think it's kind of fascinating. So then back to the notes. Okay, so then I've kind of restated what I've got here on the board. The smaller the object, the larger the wavelength. Like what we did there, an electron had a longer wavelength, much larger than a ball. And the larger the object, the smaller the wavelength. Okay, that's what I was saying. So then energy is a form of matter. Large objects have an unmeasurable wavelength, like me, or like a ball, and they display predominantly particle-like behavior. Small objects, like photons of light, exhibit predominantly wave-like behavior, and they're barely perceptible particle-like behavior. And medium-sized objects, which is blocked out here, like electrons, display both wave and particle-like behavior. So to me, I've even written this in. Very cool stuff. At least I kind of think it's pretty cool stuff. Okay, a little bit more, almost done. Not going to do too much more. Going back to first year chem, and probably on Tuesday, because I'll be up at school, I'll just refresh your guys' memory on the flame test, which we did in first year chemistry, and we looked at the spectrum of different elements, but continuous spectrum is all the colors of light are present. That's Roy G. Biv, that's in the upper right. And the bright line spectrum, only certain colors of light are produced, and that is really what's in the middle. So the continuous spectrum is Roy G. Biv, all light, pass through a prism, all the wavelengths are there. The emission spectra is when you have a gas, and this is what we did in first year chem, and we did a little lab with it, and you were able to see only specific lines, and that's because only specific wavelengths were given off. That had to do with electrons going from higher energy states to lower and giving off electrons. So I'll review this. And the absorption spectrum is the opposite. It's where the opposite of an emission spectrum. So all the colors appear except for the colors of the wavelength that are given off. So these two types of spectra are used to identify one element or compound from another. And this is how they know, like they know the sun consists of hydrogen and helium. They know what some of the moons of Jupiter consist of, or distant stars. They look at the spectra with very advanced equipment, and they can tell the different wavelengths that are given off, and they can tell you, okay, hydrogen and helium are here. That's how they know that. Now, what causes these? These bands of light are caused when electrons absorb external energy and jump to higher energy state. This is unstable, so they fall back to the lower energy level and they emit a photon of light. And that is what causes these color patterns that we see. Now, we did that in first year chem, and we and I made you guys just look at some colors, and we did the flame test, which is exactly the same thing. We did the flame test, and then we connected it to the spectral analysis. But in first year chem, something we're going to get to in our next lesson is we're going to now do calculations in determining the amount of energy given off. And we're going to go back and we're going to use these equations. So Niels Bohr noticed that hydrogen gas emitted only 4 bands of light in its bright line spectra, and these lines were always absent in the absorption spectra. Since the type of light emitted didn't shift, the energy levels that the electrons exist in must be quantized. Remember, a quantum is a definite amount. The electrons only exist in certain energy levels and can only be excited to other given energy levels. Okay, so this is going to be a good place to stop. We're going to get to in our next lesson. So what he was doing, what Bohr was doing, and he came up with what's called the planetary model of the atom, which is one you learn about in elementary school. The idea of the nucleus being in the middle and of the atom, and the electrons orbiting the nucleus like the planets orbit the sun. It's part of that we still hold with the idea of quantum definite energy levels outside for the electrons outside the nucleus, but it's deviated some, and we're going to talk about that with the quantum model. And what we're going to get into in our next lesson, probably on Tuesday on a Google Meet, is we're going to get into the calculation, and I'm going to talk about this. But this is a good place to stop, guys. Hopefully we can, with obviously weird situation with where we're at, just to finish the semester well. We're going to get through chapter 7. I've already posted the quiz, the reviews for chapter 7. And right now, I'm just hoping you guys can get caught up, and we're just going to do as best we can. I just need you to work as hard as you can with these weird times. So, guys, have a good rest of your day, and I will talk to you soon. Bye.